This year, one of the big topics at Formnext was multi-axis printing, and it actually felt like this tech is just at that point where it's moving from being a cool tech demo to actually being useful. There were tons of robot arm-based printers running plastics. Moi were extruding UV resin, reinforced with glass fiber, and then instantly cured at the printhead. Really cool process. And then there was RLP showing silicone printing that happened fully suspended in goo. But the thing you might not realize is that, the machines and the hardware are not the difficult part. It's the software that runs them, basically a slicer. So in this video, I'm talking to a young software company who make a non-planar slicer that works on anything from a 3-axis Prusa to a 6-axis robot arm. Then I've got the most compact and maybe cheapest pellet-based extruder that I think I've ever seen. And finally, I talked to a company who's already making and selling whole 3D printers, if you can still call them that, based on all this tech. Let's start with layer performance and Lukas Pelzer.
So what we do is we develop slicing software for non-planar additive manufacturing. That means we move away from 2.5D stacking layers and to fully three-dimensional toolpaths. We do this for 3-axis systems, conventional FDM 3D printers. We do this for 5-axis systems. We do this for robotic arms. And we do this independent from material. So most of our applications are in plastics, polymers, but we also can slice for metals. We have strategies for that. We can do concrete, ceramics, and so on.
What is the basic idea of how you define how the layer should look? Is that something that just happens automatically, basically gut feeling of what your slicer thinks, or is that something that I have to input as the user?
So we have multiple modes for that. You can either say, and this is the easiest part, surface quality is the most important feature, and then the slicer automatically analyzes the part and determines from bottom to top, how do I need to orient my layers, how do I need to move, to extrude material. Then you can influence that by what we call function layers, where you basically guide the layers. You define planes,
surfaces, I guess, freeform surfaces.
Freeform surfaces in 3D space, and you tell the slicer, all right, in between those surfaces, I want you to change from, let's say, flat to angled, or from angled to a curved surface. As of right now, you would create that directly in the slicer, but we're looking to expand that. So either by putting meta information into the file structure, so basically the designer can then specify where forces would apply to the part, where critical load paths are, or where surfaces are that have to be precise and perfect.
One thing I asked you about is, can you also do sort of a 3D spline through your part, where within one part you define, okay, this is how I want my nozzle to be oriented here, this is how I want it to be oriented there, or basically defining a path of force traveling through the part.
Yeah.
That's also something you can do?
With that spline mode, what we would do is basically still use our concept of function layers, just along the spline, automatically create those. So we have like a guidance for the layers. There's another concept which we use for wire arc additive manufacturing a lot, because for that you have to focus the laser point on the last layer. So you have to create a toolpath, even though this is a part with planar layers. It's a multi-axis process where we orient the tool head, guided by a robot arm, to make sure it's always focusing on the last layer. So this is another strategy based on the contour surface of the part.
Talking about the specific materials that you use. So, of course, the one that we're familiar with is just FDM, regular extrusion. This works with anything. So we've got anything that sort of lays down a layer. Be it filament, be it metal, concrete you've mentioned also. Concrete is one where that's weird, because your material isn't hardening instantly. It is sloppy when it comes out the extruder. It is sloppy afterwards. It does slowly set up, but what's some of the challenges there?
So especially for concrete, you can say it's kind of like a paste, right? So it behaves differently than a typical filament system would, in combination with the nozzle size that you have, right, which makes it really hard to control. So we have different strategies for that. One strategy is, for example, rotating the nozzle. This is
so you have a non-round nozzle. You have something that is rectangular.
Either the nozzle itself is rectangular, or you have some shaping elements on the side. So you always have to orient that into the direction that you're traveling.
So that is where the 6th axis comes into play. What are some of the limitations that you get when you don't have that many X's available, when you're going just on a Cartesian machine XYZ?
There's a maximum layer height that you can do, and then the slicer can itself define where exactly in the part do I have smaller layers, larger layers. So we change layer height within the same layer to achieve that concept. And then in terms of limitations, what we have for a 3-axis system is basically the incline of the slope that you're producing, right?
Okay, so that's a clearance angle for the tool head, essentially. What happens when your software determines that you can't work within those specifications, when like your layer spread becomes too large?
What we always have is a fallback, basically, towards a working strategy while trying to maximize the amount of strategy that the user has put in. So whether that's surface or whether that's layers oriented along the load path, whether that is support-free manufacturing, we try to do as many of those things as possible in as much areas as possible while maintaining manufacturability. Let's for example, take bamboo labs as an example, because so many people have them, right? For the X1 and P1 series, you get away with 5 degrees of slope with the stock configuration. This will take the most severe staircase effect out of your surfaces. What we have is a adapted fan shroud, so you can just print that out, stick it on the bamboo. You get to 25 degrees of clearance.
Oh, with the stock nozzle?
With the stock nozzle. The stock nozzle actually is great for non-planar that bamboo has. For typical E3D V6 style, there are volcano adapters. You have a longer nozzle with that, right? It becomes 1 centimeter longer, and then you have like 40 degrees of clearance, 45 degrees of clearance. So just by either changing the fan shroud or changing the nozzle, you get away with a lot for conventional FDM systems. If you want to go into or if you want to go above 40 degrees, you're looking at 5-axis systems.
And those 5 degrees go both ways. So it goes both towards tilting the top surface into the nozzle, where you have a smooth surface, but it also goes towards tilting the sidewalls away from the nozzle.
You have the most severe staircase with those very shallow angles, and then by tilting them away, you go more towards sidewalls, and sidewalls are actually not that much of a problem in terms of surface quality.
What gets surprisingly mind-bendy is trying to do any sort of infill, any sort of 3D pattern within a part that is not sliced in planar layers.
So we do infill. To be honest, we don't have that many patterns as you're probably used to in other slicers.
But in which ones do you really use?
What we found, what we use personally, is rectilinear and gyrite, and so those are the first 2 that we implemented. If there's demand for others, we're open to that.
I mean, rectilinear makes sense. It's just the same for every layer. It's just projected through. Gyrite, though, that gets very complex, because gyrite typically in planar layers is a continuous path. But if you scoop through like the different evolutions of the gyrite pattern, that suddenly becomes a discontinuous path. So that must have been quite a challenge to implement.
Exactly, yeah. So gyrite is not just defined in the layer, but varies with height. And so if you then try to play with that factor, play with the Z height locally, this basically becomes more or less a new parameter, not just density, but one more that you have for gyrite infill to actually tune that to however you want it.
The other specialized process is metal. And you mentioned customers have some interesting requirements or preferences when it comes to how they want to print metal with basically a MIG toolhead, is what it is on the machines.
Yeah, exactly. So metal is really interesting for repair cases, right? Because metal parts, cast parts, milled parts, typically fairly expensive. So if you have the option to use additive manufacturing to repair those parts, this is quite an efficient strategy. And we have some use cases in that. And for metals, thermal behavior is a huge topic, right? You don't want to create a thermal hotspot because you want, you would basically create just a puddle, a melt puddle.
And you would also probably deformation, just thermal contraction would be a huge issue there.
Exactly. That's another topic. And so, for example, what we can do is that we say we orient basically infill in one direction without going back and forth, or that we skip every other line to not create a hotspot there, or skip more than that and just come back.
So that is for 100% infill essentially, yeah.
We like to say that we're the first universal non-planar 3D slicer. And what we mean by that is that we work with everything that extrudes or deposits material. It means that we work with every material, it means that we work with every part, and it means that the slicer is usable from any device. So we work on computers, laptops, tablets, right? So universal in this case has basically 4 meanings.
I really like the fact that they can work with any kind of 3D printer, including simple 3-axis machines. And hey, you know who makes these? This video is sponsored, Sheedy.
This part of the video is sponsored by Sheedy and their Max 4.
The Max 4 brings a whole bunch of new features that I don't think we've seen before like this. First of all, it runs its stepper motors as servos in full FOC control mode. I recently did a video on why field-oriented control is the best way to run basically any motor, and you can even see the encoder on the back of the Max 4's motors here. Not only does this allow the motors to run incredibly fast without ever skipping a step, but it also eliminates VFA artifacts on basically any of the prints. The Max 4 also supports Sheedy's new Polar Cooler, which is an active cooling unit that keeps temperatures in the extruder low and filament from buckling and clogging, especially when using tricky materials with the actively heated chamber at up to 65 degrees Celsius. The hot end goes to 370 and the bed to 120 degrees Celsius, putting engineering materials well within the capabilities of the Max 4. Of course, the Max 4 also comes with working air filtration, uses the new 1.5mm pitch GT belts, and the whole show is run by the standard Clipper firmware to give you the freedom to use 100% of your printer's potential. Oh, and did I mention that the Max 4 is properly big? It has a 390 by 390 bed and will print up to 340mm tall. Sheedy are throwing in a free Polar Cooler if you order a Max 4 or a Max 4 combo with the 4-filament Sheedy box before December 8th, and you can find all the info below.
Thanks again to Sheedy for sponsoring this part of the video.
Okay, next up, when you start going to multi-axis machines, you're most likely also going towards a larger setup. And once you have a robot arm, it suddenly gets trivially easy to build a setup large enough to where feeding it filament kind of stops making sense.
The first step to this is getting some sort of material into the printer, and the typical way to do it is with pellets. And you guys are doing something that is a bit different than the larger ones that we're going to see in a minute. You're actually building a small one.
Exactly. So we are Metexon. We build small pellet extruders. It's basically the same principle as the large ones, but a very small form factor.
So this feeds standard pellets through an air hose, and it extrudes it with a standard E3D V6 nozzle.
Exactly. Yeah.
What flow rates are you getting with this?
800 grams per hour.
Which is way more than any hot end you'll ever see.
That's true.
And it is so compact. So let me give you a walk around.
So yes, Metexon are mounting the MTX6 to their own Clipper-based Core XY machine, but the extruder can handle tilt on a robot arm between 30 and 45 degrees. Pellet extruders come with the unique challenge of using a source material that you can't really just push or pull into the printhead. So most extruders choose to blow it into the toolhead.
So even though this is a tiny pellet extruder, they can still feed standard industrial resin pellets, which is up to 5mm. I'm just going to reach in here and hopefully not shred my fingers. But these are the standard pellets that you use for filament making and for any other extruder as well. The feeder portions them into little bits and then blows them through this air hose up to the extruder where there is a small little feeder, little hopper.
Then the pellets get pulled into a custom 10mm feed screw that is engineered to be as small and as lightweight as possible while still allowing in standard pellets of up to 5mm in size. This screw took them quite a few iterations to get right, and while building larger extruders is a fairly standard endeavor, at this size, the textbook solutions just don't work anymore. The small size also has some interesting usability benefits. They're using standard V6 nozzles, and you can use retract and pressure advance with the extruder. Typically, that just doesn't work with direct pellet extruders. Because they use a stepper motor to run the screw, Clipper is totally happy to run it just like any other extruder. Though their killer feature is TPU. No filament, no worrying about filament kinking and blocking the hot end. Their extruder works with TPU as soft as Shore 40A. Typical flexible filaments never leave the harder D Shore scale, and the softest one on the A scale managed to do 60A, not 40. And those are not really printable without massive effort and slowing down a lot. The Metexon extruder can comfortably run TPU at 300 grams an hour. Now, their setup is obviously intended for business or industrial applications, but Doing a bit of napkin math, if you're printing parts from softer flexibles, this extruder is going to pay for itself in less than 2 weeks of runtime, just in savings from being able to use Shore 68 pellets instead of filament, and not including the increased throughput of the machine itself. Exact pricing is RFQ, so I'm not going to spill the beans here, but I was told the price and it is significantly cheaper than I would have expected. And while it's maybe not as necessary as with larger extruder setups, Metexon are working on adding a drying function to the pellet feeder. But overall, this extruder is the same working principle as those 6x6 robot arms in their printer cells. And we're going to actually look at Caracol next to make exactly those supersized printers, if you can still call them that. Interestingly, these large-scale robot arm-based machines are still much more of a modular concept typically, where one company sells you the arm, another sells you the extruder, and then yet another provides the slicer. But Caracol were, I think, one of the 2 companies that provide an all-inclusive package, basically.
The reason why we chose robotics in the first place was the flexibility also in terms of freedom of geometric possibilities. One of the most common, I would say, solutions when printing with robotics is printing 45 degrees. So instead of just tilting to one side the angle of the print, and this allows you to print things such as the catamaran that you see there. Caracol is a large format robotic 3D printing company. We offer turnkey solutions, basically including everything from hardware, software to automation. So we developed our own slicing software as well as our own IoT software to be able to control everything. And those are our ADOS Builder and ADOS Nexus. And so in that suite, basically we can offer the full comprehensive package to be able to control the process, the way that you approach the slicing. Polymer, we use an FGF process, so pellet-based technology. What you see basically is the material is kept at the back in that hopper. It allows you to dehumidify and keep the material at the best temperature for the specific material that you have inside. Then it goes automatically into the extruder, and it's automatically called, and then it allows you to continuously print without ever interrupting. So there is no human intervention at all during the whole of the print. This is a 3 meters by 1.5. So this is an advanced type of print bed. It's not the most commonly used. We have other types which are more economical, especially on the large scale. So, for example, the boat was printed on a large metal print bed with some wooden panels. So very simple setup, but which allows you to scale. And our system can go up to 10 meters in scale on the x-axis. So you have a very broad print bed. So in this case here, what you're seeing is our heated print bed. So this is currently at 80 degrees Celsius. This really helps ensure that the material is sticking to the print bed very, very well. For these type of large-scale solutions, it allows you to be flexible in having one print bed, switching it out to another, and similar. We can put the system on a rail, we can put it on a plinth, the way that this is, so that you can extend the height and really get the maximum bounding box out of the volume of your robot. We had a lot of know-how on the robotics side, and so we saw that some of our customers were requiring some applications that were a bit beyond what polymer could provide, and so we decided to introduce metal, still leveraging the same concept and same type of platform that we have on the polymer side. So Vipra is our wire arc additive manufacturing system, so DD type of technology. We have 2 types of head. One is a CMT-based technology, which is what you see here. We also have a plasma-based technology that allows you to achieve even better, finer quality in the type of print. We have a lot of control sensors and in the head, so that's part of the development. It's not just the torch itself that you're using for the welding process, but everything around it, of course. Here, for example, you see there is an additional robotic element, which is this external manipulator, which allows you to tilt the parts so that you're always parallel to the ground, basically, and giving all the input and data on how the process is working. And here, of course, the key aspect is that you need to work with the part so that you can really ensure that the part is always positioned in the best way for the welder to effectively go through its layer. Here with the CMT head, some of the most common materials are, for example, stainless steel, nickel alloys such as Invar, copper, we use aluminum, so kind of a broad, we're extending every day, let's say, because our team works a lot on processing, qualification and characterization of materials. I mean, we're definitely looking into how to automatize this further. For example, a lot of the innovations that we're presenting this year at Formnext are related to ensuring that the workflow for customers is as automated as possible. So we've started with features such as, for example, controlling also post-processing operations, but definitely the idea is also then to automate on the other side, so when the CAD comes in. The other thing that we're working on is AI, giving some automation and features that allow the machine to learn also from what it is doing. So there are some cameras on our extruder, thermal cameras, visual cameras, that pick up all the information and basically match it with the patterns that it's supposed to have in terms of the print. It's a first introduction, so of course the machine for now will still move according to the program that has been set up. Then as we move forward, as the AI feature improves, then the automatic corrections is something that will come up later, let's say. It's still, of course, there is some knowledge to be built on the way you design parts for these types of processes, and that is what we try to do through our team, to train the customers if they don't have that experience internally already. We try to provide all the knowledge they need to best approach these types of technologies with the engineering of the parts beforehand.
Of course, everything in this video still solidly falls in the B2B sort of industrial scope. Like anything else that has more of a niche application, it just makes sense that the tech is first developed and employed for those niches where it provides the biggest benefit overall. But just getting a sense of what's already possible has given me a ton of ideas for things that might work on our smaller printers as well. That's it from Formnext from me. As always, take care of yourselves, keep on making, and I'll see you in the next one.